Thanks for the friendly introduction. And thanks for having me. I'm going to talk about some fairly general topics, and I'm relating to some stuff that's a bit more specific that I've actually in the past. And I want to investigate the question of how to understand what the problem actually is with black box algorithms for machine learning, or how it relates to understanding more generally. Before that, I would like to devote one slide to the people in my wonderful project, which is just started basically 2 months ago. I now have a postdoc and a PhD candidate. I think that's from Düsseldorf originally, or has done a PhD in Düsseldorf. Düsseldorf Center for Logical Philosophy of Science, has a background by chemical engineering, and it's going to work on the use of AI and XAI in protein structure prediction, quite obvious topic, I would say. And Frauke is from Bonn, from Dellsén, you know him. And she also has a background in physics and is going to investigate how AI and AI are used in particle physics. So these are certainly two people who will look up. Good. So now down to business, basically. So so we all know that there's kind of like a lot of predictive success with these deep learning, in general machine learning models, but mostly, of course, deep learning models, most commonly. And like an obvious thing about that is that some parts of that are typically black box. So when we see these diagrams, as for instance with AlphaFold 2, here we just get told that there's like this evoformer that works in some mysterious way, and then we have the structure model with something, and then out comes the wonderful structure prediction from amino acid sequences. So of course, yeah. So in very often, on many levels, this is being black box. Many of us don't know what exactly is going on. Okay, so of course you can read the technical supplement, and maybe you'll be able to digest with some effort what's going on there. So in a sense, you could say like these models are often algorithmically transparent. You know what the algorithm is doing if you spend enough time. But the question is that what does it really tell us? So does it really answer the questions that we want to answer when we ask, how does that work? So what's a machine learning model? Very generally speaking, you have a space of data, call that X, and then instances from that space are typically given as some sort of multi-dimensional vector, or it could be a tensor, which is mathematically also a kind of vector. The entries of that somehow characterize features of some system. If we use it in science, at least, for instance, if it's pixels on an image, of course, that's going to like show what the object looked like in that image. If it's more abstract vectors, such as, I don't know, transverse momentum, particle sheet, and so on, the component is the transverse momentum of a particle. Then you have some sort of output space, which could be just a classification, but it could also be like some digestion of X, could be like some processing of X into a different kind of image, for instance. It could be some, as we saw, like some rotatable 3D structure. And the model is basically just a parameterized mapping that gives you an estimate of what the best sort of response to a given data point X is. So far, so good. So now we can think of machine learning models, specifically neural networks, as these sorts of mappings, maybe complicated looking mappings, with pre-parameters that we adapt. And this adaptation then is called the learning, because we somehow leave some freedom in there how exactly it works out. So one sense of black boxness in machine learning is, of course, that a black box model is some sort of function that's very complicated for humans to comprehend. This is what Cynthia Rudin says. A kind of similar characterization of opacity in general has been given recently by Räz Beisbart. He says a method is opaque to the degree that it's difficult for humans to know and understand where its outcomes arise. So here you can see there's kind of two things going on. On the one hand, we may not be understanding like the kind of function that's being instantiated here. We don't know what it says basically. On the other hand, we might wonder about particular outcomes that this function has. Of course, Katie has given like this taxonomy that everybody now cites, where you would think about the algorithmic functioning as a whole, which is basically, I guess, what Rudin has in mind here. You could wonder about how this is realized in code, so be a bit more specific. Or you could really focus on one particular instance, and then maybe especially on the outcome. So first, we go back. One thing that gets sort of is somehow in there, but it's not extremely specific, is the element that goes back to Paul Humphrey's seminal definition that you somehow have a relativization to the agent. So what's opaque is always dependent on who's asking basically, or who's looking. So Humphrey said this definition of process is typically opaque relative to a cognitive agent X at some time t, just in case X does not know all of the at t, and it's always essentially opaque all the epistemically relevant elements of the process. So this is interesting because there's also like this condition that in some sense it's epistemically relevant for the agent to know that stuff that's in the process. So Juan Duran, for instance, here has focused quite a bit on this part of epistemic relevance and kind of suggested that lots of things are irrelevant to us. We don't really have to know many details of large-scale simulation models or maybe even AI models. And he suggests here, imagine this fictitious case where some researcher knows every detail of the workings of some physical computer, including the software run on it. And would that researcher benefit from this excess knowledge, or instead would this be a burden for the justification of results? So Juan here reads this as, well, what's epistemic? Well, kind of something to do with knowledge, right? And what's connected to knowledge? Well, justification. We want to say whether we can somehow, we want to have reasons to trust what comes out of these actions. And so maybe we don't need to know all these details. That's not the right level of detail to look at, but maybe some coarse graining. And then Juan has this idea of computational reliabilism, which is, well, not really reliabilism, but basically says, don't focus on what's going on inside, just check whether it works. Okay, so that, I think epistemic relevance opens up like a load of possibilities because we have many cognate notions to knowledge, not just justification. So the question with epistemic relevance really is, what do we want from these machine learning models? Sure, knowledge applies justification, so we want to have some justification for saying, yes, I know that because it came out of this very reliable algorithm that I, for some reason, can say it's just spits out outputs and justified to me. This can come from cross-validation and robustness analysis, so it doesn't have to lift this black box nature. But there's another point, namely that some epistemologists, and I tend to agree with them, have argued that knowledge is valued for the sake of understanding, which is not necessarily, some people think it's a species of knowledge or it's like a specific kind of knowledge. Some disagree because we could say like, well, it just needs to be tethered to the facts in a much looser sense than we would require from knowledge. So in principle, you could say, well, we want to understand stuff, therefore we want to know something about machine learning that helps us understand stuff. Of course, that always, not always, I mean, some argue that explanatory understanding is derivative of like this more objectual understanding where you have the whole topic that you understand, or that these can coexist, but very often the claim is that at least scientific, specifically scientific understanding is explanatorily bound, as it were. So there comes the relevance of XAI for us as philosophers of science, right? We could be interested in that because we could ask what can it deliver for us? What can it help us understand better about machine learning and maybe AI in general? But that doesn't answer much because for what sake do we want to explain and understand either the model itself or its outputs? Good. So here comes Humphreys again. Humphreys is the one to have basically paved the way for thinking in terms of stakeholder perspectives. For instance, Páez had a fairly early paper where he says the purpose of providing an explanation or interpretation of a model, he's here thinking of machine learning models specifically, or decision, is to make it understandable or comprehensible to its stakeholders, somebody who wants something from that model. Same thing with Lena and her group. They have a paper where they try to specify that in more detail and specify certain goals, expectations, needs, demands, which they then collectively called stakeholders. This is the RADA, one from that model. Similar thing with, maybe they don't need to do this so much detail, but Carlos Zednik has this, like gives an example of what different stakeholders could be. For instance, when you have like in a bank, if you're using some sort of algorithm to test whether somebody's worthy of getting a credit or give them the credit and not lose your money as a bank, then you have different roles. Operators are people using these algorithms to get out some sort of output, and they want to understand what they're doing, maybe to estimate what their functionality is. Then you have executors who are supposed to take these outputs and interpret them as some actual value of risk that you could associate with the given subject. An examiner is supposed to determine an overall measure of reliability and whether that system is functioning legitimately. And then you have like the subjects, so either these people who the training is based on, or people who are currently being decided upon whether they get the credit or not. And they want to maybe understand what went wrong, why did I not get the credit, what could I change? Good. So this has been picked up by Oliver Buchholz from Tübingen. He says, yeah, for instance, you have this line, which I think everybody maybe knows, like this local approximating XAI thing where you just locally approximate the model and then somehow map out the features that were relevant for its decision at that point of the decision. You have this list, and then you kind of understand one particular output. This could be interesting for users, but for data subjects, it might be more interesting to understand, well, what would I have to do differently to get like a different output? So counterfactual explanations, as they're called, where you check what happens if I do like a small change in the X space, what happens to my Y? This is more interesting to data subjects. So there actually you can really map this to different stakeholders. So Oliver tries to understand this in terms of like this means-end epistemology, where you have rational agents, they have certain epistemic ends, they want to know something, and then you can kind of suggest means that they ought to adopt in order to achieve these ends. Here he maps this to XAI and says, well, we have the topic that is explained to the stakeholder for some specific goal by means of some specific instrument. Fine. And then he says, like, the aim of, I think, XAI is to provide instruments that produce explanations for some topic, for some stakeholder. And then this can be a particular aspect. So some explanations deliver this, some that, and so on. So he tries to give like a small framework which summarizes all these insights that we just had. But we're back to square one, because for what sake do we want to explain and understand even particular aspects? No, it doesn't tell us a lot. It just gives a rough framework of what's going on here. Good. So I here want to distinguish between proximate and ultimate aims. I take inspiration here from a very famous debate in philosophy of biology. So Ernst Mayr had this paper where he says, like, well, imagine that you have like this warbler and it migrated on the 25th of August because the cold air with northerly winds passed over the area, and so the bird was somewhat prompted to move. Now, the physiological condition of the bird interacting with photoperiodicity, the drop in temperature, etc., these are the proximate causes of the migration, but ultimately, of course, it's the lack of food during winter and its genetic disposition, which causes it to behave in a certain way that makes it survive and have offspring that do the same thing. So I'm not sure whether these are necessarily ultimate causes, but certainly they're more distal causes, and they could, relative to evolutionary theory, be seen as, in some sense, ultimate. I would suggest that we can use that distinction and rephrase things in terms of aims, even though maybe in the evolutionary context it becomes a bit iffy because you buy into some sort of teleology. But anyways, you could say, like, in some sense, the proximate aim of the bird's behavior is to just avoid the cold weather to get more food. But ultimately, it aims to survive and reproduce in some sense. I think this behavior is geared towards making it survive and survive. Okay, so providing instruments that explain certain aspects to particular stakeholders is certainly a proximate aim in pursuing or deploying these XAI methods. But what's the ultimate aim? What do we want from that? And when we want to explain what's going on in AI. I would claim, here's some axiomatic claims of the word. I think the ultimate aim is not uniform. And I think this is compatible with the stakeholder perspective. But contrary to the pure stakeholder perspective, it co-varies with the context of deployment rather than the individual. Furthermore, it doesn't have to have anything to do with explanation, but it could. And I guess, sorry, in science, it's important to recognize that inside of machine learning science, proper. It's important to recognize that the ultimate aim is to understand the subject matter that you analyze using AI. It's not you don't really care that much about, well, it could be beneficial for some reasons, but it's not what you ultimately want. You want to understand, why did it succeed? Why did it predict proteins like that? What was going on? What did it find? Okay, let me give you some examples. In medical practice, for instance, there's an interesting paper that was published in some Nature venue, and they had like a conference, and they also followed the following question. Suppose you have cancer and need surgery to remove the tumor. Which of the two surgeons would you pick if you had to choose between a human surgeon with a 15% chance of dying, or a robot surgeon with only a 2% chance of dying, with a caveat that no one knows how the robot operates? No questions may be asked. Who of you would pick the robot? Yes, I would too. But in this conference, all but one were, because I don't know, maybe they suspected that, like, maybe the testing is not representative or so, and yeah. But maybe the way the example was set up is like you're supposed to believe that there's really the chance of dying, like in some objective sense. Anyway, so it seems like that some people argue based on these observations that it's very important to solve this explainability problem with these partly black box algorithms. And it's important to ensure these trustful human-AI teaming relations in medicine. That's what they claim. So in other words, in the context of medical practice, not research, the ultimate aim seems to be like the consentful deployment of, for all we know, the most reliable methods. We want to maybe automatize certain things, knowing that they can operate better. Maybe here, noisiness is not such a good thing. Like if you disagree with the with the scaffold, then maybe it's not so good. And here, XI serves the proximate aim of making AI methods appear trustworthy because we think we understand what they're doing. But ultimately, it might increase the acceptance of more reliable methods. That's what we're actually aiming for. So we don't have to care necessarily about whether we really understand what they do. We just want to increase the acceptance of them, assuming that they work better sometimes than we do. Another example. So I'm not saying that these are excellent examples, but they make clear what I want to say here. Here by people also from Lena's group actually involving Eva, but also from Dortmund. They have this example from like a legal/ethical context where they say that assume that you have like a company with this fully automated hiring process, which screens, ranks, and selects these job applicants. And then you have April, some agent applying for the job, and she's in the last place and being excluded from this hiring process. So maybe this was decisively influenced by the fact that she's a black woman, which, as we all know, can happen with these adaptive biases with these ML systems. And so the worry arises that you can't hold anybody morally responsible or legally accountable because, well, we don't know what's going on in the ML. So if, on the other hand, that's what these guys argue, if some human decision maker had a simple explanation of how the recommendation has come about, then he or she would be in a position to bear direct responsibility because she knew what was going on. So this at least delivers kind of a sufficient condition. Maybe it's not necessary to have the explanation, but it would be sufficient. If you know what's going on, if somebody can explain it to you in digestible terms, you still say, well, I don't want to hire her. I see that it is because she's a black woman. Then people can come and say, sorry, but that's like, you're discriminating. Okay, so in the context of moral attributions, legal claims, the ultimate aim seems to be the localization of responsibility or accountability, and XAI here serves the proximate aim of making reasons for decisions transparent so that we can hold people. Yes, okay, so that I had that. So now to science. I'm a philosopher of science. I'm interested in what's going on in science. And so what's the aim of science? Well, luckily, the University of California Museum of Paleontology has like this non-profit website where you can look at how science works. So they say right away, science aims to explain and understand. Full stop. Cool. Good that we know that now. Okay, jokes aside. A couple of philosophers of science have recently claimed that in some sense, understanding seems to be one of the major, if not the major aim of science in some sense. Here's Catherine Elgin, whose work is kind of complementary or really rival to Henk's work. Actually, here she says, although it's not science only objective, I would call understanding it epistemical. Somehow, you can reasonably argue that this is the thing that science can get at and that many people want from science. And it's most straightforward, it's the aim of science is to explain phenomena to generate understanding. I found this interesting book by somebody named Bert, where he says like the aim of science is to use scientific knowledge. Okay, so that means trouble for what I'm claiming here, but maybe we could say, if we accept that knowledge is valued for understanding, which could be weaker, more encompassing, but still weaker, then we could say, well, maybe knowledge is valued, or we want knowledge from science, but maybe it's just a proximate aim to get this overall map that's more akin to understanding. We can discuss about that, but I think my account can please be saved. Here's another troublemaker, this guy named Rowan. Here he says, like, okay, science doesn't have aims, people have aims. Yeah, it doesn't make sense to talk about the aim of science. In what sense can we take it to talk about the aim of science? Well, he comes down with the verdict that we could talk about hypothetically rational aims. So, X is a hypothetically rational aim in doing science, even only if doing science raises the reliably, makes it more reliably plausible that you achieve X more than any other activity. Yeah, okay, so understanding is often said to be measured or determined by means of ability. Lots of people claim that, and you could say, like, given practical success, like this computer, this laser, the phones that we use, etc., new experiments that seem to show what they're supposed to show and so on. Science, at least, seems to be reliably increasing understanding of the world as a whole more than any other activity. I would think This is something that many of us agree to. And I would also say, like, if you ask enough scientists, I don't know whether anybody has done that, but empirically it could be that most scientists would say, yeah, we want understanding of science. I think it's plausibly the majority vote, and also in that sense, like the aim of science. If they have to agree on something, it's they want to understand. Okay, a couple of questions. Is there only one aim? No, no. We already there's only one aim. Just understanding always connected to explanation. What's the target actually? Okay, so the first one, not necessarily, but as I said, maybe it's the overarching aim or the most plausible thing that could be called the aim. Is it always connected to explanation? Not necessarily, but still, I would say maybe there's some sense in which really scientific understanding is always connected to explanation. Maybe you could take that case. And the most interesting question here is, what's the target? What do we want to understand? So many people like Henk and Michael Strevens have made a distinction, like understanding a theory is somehow, in some sense, being able to use the theory for certain purposes, and understanding a phenomenon means using that theory to leverage explanations of that phenomenon. Michael Strevens makes similar distinctions and said understanding with the theory means to be able to use it to explain phenomena and then get understanding phenomena. Maybe we can start with models instead of theories, maybe a loose initial theory makes sense of that. But in the machine learning itself is usually the target, not the vehicle. You know? That seems strange. So how does the experiment are demand to increase understanding of phenomena, scientific phenomena? I think you could make out three distinct paths to getting to scientific understanding using XAI, or maybe not using XAI, but using machine learning directly. So one path is to explain the model and then discover something about its discovery method or prediction method. So how did AlphaFold come up with these predictions? Well, it uses information XYZ, and okay, that's interesting for us, and then maybe we can start thinking about using that as well, integrating it in a big context of scientific investigation, and then reproduce that somehow and gain understanding. Maybe we can also try to look more directly at the outputs, so reproduce the model's predictions with some alternative model that's somehow based on some very selected elements of what we found out about the AI. Yeah? We don't have to understand it as a whole or how it predicts, we just have to find certain pieces of information about it that enable, and I will give you an example later, the generation of more explanatory, that we consider explanatory. Or of course, you could maybe use the ML directly to understand facts or dependencies in the world, but that would not involve XAI, and I think it's kind of a limited sense of understanding. I will just briefly go into it in a minute. Good, so here's the situation. We have our scientist wondering about a certain mysterious and colorful phenomenon, and not understanding this black box model, and somehow she has like this prediction from the black box model, and okay, so she can kind of handle and process information about that phenomenon. So now comes the XAI, and maybe she understands the XAI model pretty well, and therefore gets some fair amount of understanding of the ML model as well, but that doesn't by itself clear up how the phenomenon works. So maybe we could have XAI, sorry, this should also say XAI here. Maybe we can have like a well-understood XAI model that targets more this prediction method of the ML and leaves other things about it in the dark. And thereby we get some amount of understanding at least of the phenomenon itself, because we know how to address it better. By the way, here you can see that like the machine learning success itself becomes like this intermediate phenomenon that we first want to explain, and by means of that explanation, you maybe get to better explanations of the ultimate phenomenon. Here's the other route. You could just try to understand certain very specific aspects, so not so much about the ML model, and then use that information to build like an additional theoretical model, and that will help you to understand a fair bit about the phenomenon, ideally, if you're lucky. Or finally, you could just bypass the XAI step altogether and just look at how the model predicts and classifies, and thereby have like maybe this more general understanding of the phenomenon right away. Good. So I here want to draw on previous work, and here I point this. How much time do you have left? 5, 10?
5 minutes.
Okay.
I was meant for 10 minutes of discussion.
Yeah, great. So I point this notion of what opacity. I think this is the key thing that's new with machine learning, or especially deep neural networks, that you have some sort of information that's already there in the data, and the DNNs are able to pick up on that and form, like, will correlate some activations of nodes or so with that information, for instance, or patterns of activation across the network. So they kind of find out something new, as it were, but we don't exactly know what it is necessarily. Here's a nice example. Particle physicists have for instance, train neural networks on simulated data to classify whether something is a signal data or a background data. So background is like the null hypothesis, no new particle of interest or so. And the signal is, yeah, there is a particle of interest. Here you see like you have this characteristic bump. When you use the simulated data to plot a histogram, the bump says, well, there's too many events here. There should be like this additional process which involves like this perpetuity particle. Now what they did was like just train DNA classifier to classify a single background without telling it about anything about these mass histograms that you can reconstruct using physical laws. Yeah? Just get like tracks in the detector, they have momenta, and then you can, through relativistic energy momentum conservation, can infer back to the mass in a nonlinear fashion actually. They plane away this information. Yeah? So in this histogram, you see right away what's happening. You weight each data point by 1 over the height of the histogram to get like a uniform distribution. But notice that the changes in these other histograms are quite subtle. You don't see something is different, but you would still say, okay, so in these other variables, even though I've done something massive to the data regarding the mass information, with these other variables that are plotted here, you don't see that big of a change, or you see some sort of change, but it's not easily interpretable. So fairly little, so this doesn't involve looking into any hidden units or weights or biases or even necessarily the training, just make sure that it works in the first place, and then later you see that it doesn't work anymore when you take away that information. You know, so it failed to classify it, so it somehow has recovered this more involved physical information. So fairly little is understood about how the machine does it, or has learned the information. And a lot is understood about what it is that it's picked up on. Somehow it's got this like a statistical information that we call like the mass bump. So here you could, if you knew that, if you know that now, you can somehow maybe generate like an additional theoretical model, like some Lagrangian, term from Lagrangian, that in some sense might be more explanatory, and then you understand better what's going on in this particle domain here. But of course, this involves additional modeling steps. You have the data, you process it somehow through neural network that just represents like a distribution of signal to background or so. And then when you find out what's going on inside, or what's the information that it has picked up on in the data, not necessarily what's going on inside, then you can start maybe modeling making new physics models that then would explain this phenomenon in some sense. Here's another study where this was done in a similar way. They trained like this some sort of autoencoder architecture with a sparse layer where there's only a few nodes to predict the positions of a damped pendulum, simulated damped pendulum, and succeeded in doing that. When they plotted like the activations in this very condensed layer where there's only 3 nodes, they found like perfect correlation with certain quantities, which are the determining constants of the equation, of the harmonic oscillator equation. So somehow the neural network learned about the damping constant in the spring constant. Yeah? That's what it looks like. Here you see like this linear correlation with the damping and with and the spring constant anyway. The third one didn't do anything in relation to these. Okay, so one method here we see how it does it. It stores the information in the innermost layer, but at the same time also what it has found out. So these two things are conceptually distinct, but of course XA can cater to both, and very often it will conceptualize this in terms of like these 2 independent dimensions, and you could think of the total opacity as a function of that you can reduce either along one dimension only, or usually will reduce it along both. But I said that there could also be, then I'm done, understanding without explanation. So what about that? Yes, this would be this situation. We just look at the classification that you get out and then understand something more about the phenomenon in question. And of course, Emily is most prominent for having promoted that this is kind of what happens there. You are. Right? Some people have criticized that this might give you a fairly limited sense of understanding, and Klaus and Tim suggest that maybe only this kind of objectual understanding. You don't really get any sort of explanation, or get necessarily an explanation, but you just understand the field as a whole better. I tend to kind of agree that this might be a good way of looking at things. Like the direct understanding that you get from machine learning is usually rather, I understand the phenomenon as a whole better, I understand the field better. Unless you interpret unless you find methods to explain certain aspects. Maybe Dellsén's view of objectual understanding as this dependency modeling is helpful here, that we gain like this new mass of dependencies in the world by looking at how AI does it. So conclusions in science understanding, ML itself is merely proximate aim. The ultimate aim, arguably, is the understanding of scientific phenomena. Sometimes fairly little needs to be understood about machine learning itself, only what it has picked up on, not necessarily how it does that. And if we bypass XA altogether, maybe we only get like this limited sense of objectual understanding. Maybe let's talk about that. Thank you.